Welcome back to the Robot Papers. In episode 1, we explained the paper. Today, we actually run it. I'm going to walk you through everything you need to get GR00T N1.6 working on your own robot from zero to inference. Okay, let's dive into this. We're going to cover the whole pipeline, from getting your environment set up, to prepping your own data, fine-tuning the model, and then, the moment of truth, getting it running on an actual robot. All right, first things first, let's get the launch pad ready. This is all about getting the code, the dependencies, all of that installed. Think of this as pouring the foundation for a house. You got to get this part right or everything else is going to be a headache. So the GitHub repo lays this out in 5 pretty clear steps. First, just the basic sanity check. Make sure you've got an NVIDIA GPU, CUDA, and Python 3.10. Now, step 2 is a huge one, a really common gotcha. When you clone the repo, you have got to use the -recurse submodules flag. Don't forget it. The project uses UV for dependencies, which is super fast. Then you'll just go grab the GR00T N1.6 3B model checkpoint from Hugging Face. Look, if you hit a wall during install, it's almost definitely one of these 3 things. You either forgot the submodules flag, your CUDA and PyTorch versions are fighting, or a library like Flash-ATtn is failing to build. What's the common theme? Get your environment, especially your CUDA toolkit, set up correctly before you run pip install. It will save you so much time. Okay, setup is done. Now we get to the most critical part, the data. The whole point of a foundation model is to teach it new things, and that means GR00T has to learn from your robot's unique experiences. Groot basically thinks in these little data packets, these triplets. It needs 3 things: the video from the robot's camera, the robot's own state, that's proprioception, stuff like joint angles, and then the action, the actual command you sent to the motors. This triplet is how the model connects what it sees to how it feels to what it should do. And this is just fantastic news right here. You don't need a massive Google-sized data set to get started. Because the model is designed for data-efficient fine-tuning, you can start seeing real results on a single task with just 20 to 50 good teleoperation demos. That's it. It makes this whole thing way more accessible. So your data needs to be in what they call the GR00-flavored LeRobot V2 format. But look at that last file there, modality.json. This is the secret sauce. It's more than just metadata. It's like a dictionary that tells the model exactly what every single number in your state and action data means. This little file is the key to GR00's cross-embodiment magic. With our data ready to go, it is time for the fun part. We're going to bring this model to life. We'll start with zero-shot inference and then jump into fine-tuning. Okay, you have to understand this concept, the Embodiment ID. Think of it as GR00's way of asking, which robot am I controlling right now? This ID tells the model to load a very specific small set of neural networks that act like translators for your robot's unique body. This is what allows that one giant core model to control everything from a Unitree G1 humanoid to a simple desktop arm. It's brilliant. When you run inference, you've got this classic trade-off you need to manage, speed versus quality. And you control that with the number of diffusion steps. For real-time control on a physical robot, you want fewer steps for lower latency. For an offline analysis where you just want the best-looking motion, you can crank it up. The paper found that about 4 steps was a really nice sweet spot that worked pretty well for all their robots. Now, to actually fine-tune the model on your data, you're going to run a command that looks something like this. Using the launchtrain.py script, the 3 most important things you need to give it are, of course, the path to your dataset, how many steps you want to train for, 20,000 is a good place to start, and, you guessed it, your robot's unique embodiment ID. So, you ran fine-tuning. It finished. Now what? How do you actually know if it got any better? Well, you benchmark it. And the repo comes with awesome built-in support for standard simulators, so you can get real hard numbers. So you can take that checkpoint file you just trained, drop it into an environment like RoboCasa, which has all these kitchen tasks, and it'll spit out a success rate. This lets you see exactly how much better your model is compared to the original baseline one. And this right here is the goal. This is what you want to see. A chart where your fine-tuned model, trained on just a handful of your own demos, blows the baseline model out of the water on tasks that actually matter for your robot. This is that sim-to-real workflow paying off. All right, now for the final boss, running the GR0 policy on actual, physical hardware. Let's talk about how to bridge that sim-to-real gap. At a high level, deployment is really about connecting two pieces, the GR0 inference server and your robot's own controller. You're basically just going to pipe in the camera feed and the joint states, and GR0 is going to send back the motor commands. The one thing you have to watch like a hawk here is latency. End-to-end latency is king. And this is the loop it has to run, in real time. From the light hitting the camera all the way to the motors turning, the whole thing needs to be fast enough for the robot to react smoothly. The team reports inference times around 27 Hz on an RTX 4090, which is definitely fast enough for real-time control. Okay, to wrap this up, let's go over a few pro tips, some lessons learned from the field that'll make your whole journey a lot smoother. Okay, listen up because these are gold. 1. Absolutely install Flash-ATtn if you can. The speed boost is legit. 2, and this is huge, always test the base model's zero-shot performance on your task before you waste a single second collecting data. It might already work. And 3, use the simulator. Use Isaac Lab to generate tons of synthetic data to add your real-world demos. It's a total game changer. And that's really the big takeaway. The barrier to entry for this kind of general-purpose robot AI has never, ever been lower. The models, the code, the simulators, it's all out there. So there you have it, the complete playbook from cloning the repo to running on hardware. The only question now is, what are you going to build? What's the first skill you're going to teach your robot? Thanks so much for watching. On the next Robot Papers, we are going to put all this theory into practice. We'll fine-tune GR00T live